2022, NASA released an audio recording that went viral. It was the sound of a black hole, a deep, haunting moan, like something from a horror film, echoing across 250 million light-years of space. It racked up millions of plays. People called it terrifying, beautiful, otherworldly. But here is what most people do not understand. That sound should not exist. You have probably heard that space is silent, that in the vacuum of space, no one can hear you scream. And that is true, mostly. But NASA has been recording sounds from space for decades. They have captured the whisper of Martian wind, the chirp of colliding black holes, the eerie hum of interstellar space. And what they have discovered challenges everything we thought we knew about the cosmic silence. Space is not as quiet as you think, and the sounds it makes are stranger than anything you have ever heard. With what you learned in school, sound cannot travel through a vacuum. This is fundamentally true. Sound is a mechanical wave. It needs a medium to propagate. On Earth, that medium is usually air. The vibrations from a guitar string push air molecules, which push other air molecules, which eventually reach your eardrum and are interpreted as music. In space, there is almost nothing. The average density between stars is about 1 atom per cubic centimeter. For comparison, the air you are breathing right now contains about 25 billion molecules per cubic centimeter. Space is, for all practical purposes, empty. So how can NASA record sounds from space? The answer is, they are not recording sound in the traditional sense. They are doing something far more clever and far more revealing. They are translating the universe into frequencies our ears can understand. Visual, comparison animation showing sound waves traveling through air molecules on Earth versus the near vacuum of space. Show density comparison with particle counts. Transition to electromagnetic spectrum visualization. NASA calls it sonification, the process of converting data into sound. Here is how it works. Telescopes like Hubble, Chandra, and James Webb do not capture photographs in the way your phone does, but they detect electromagnetic radiation, X-rays, infrared light, radio waves that is invisible to human eyes. Scientists then translate that data into colors we can see, creating the stunning images we associate with space. Sonification does the same thing for your ears. When NASA sonifies an image of a galaxy, they might assign lower pitches to objects near the bottom of the frame and higher pitches to objects near the top. Brighter regions become louder, dimmer regions become quieter. X-rays might be represented by brass instruments, while infrared data becomes woodwinds. The result is a musical interpretation of light, not actual sound waves traveling through space, but data made audible. The Crab Nebula, for instance, has been sonified using data from 5 different telescopes spanning the entire electromagnetic spectrum. The radio waves become the lowest tones. Optical light occupies the middle range. X-rays are the highest pitches. When you listen to it, you are hearing the entire energy signature of a supernova remnant, a star that exploded nearly 1,000 years ago, still radiating across wavelengths from radio to gamma. You are not hearing space. You are hearing what space looks like, translated into something you can feel. Now let us talk about the black hole sound that everyone heard. The Perseus galaxy cluster sits about 250 million light-years from Earth. At its center is a supermassive black hole, millions of times more massive than our Sun. And in 2003, astronomers discovered something remarkable. The black hole was singing. Not in the poetic sense, it was producing actual sound waves. Here is why. Unlike the empty void between stars, galaxy clusters are filled with hot gas. Hundreds of galaxies, each containing billions of stars, are embedded in a vast cloud of plasma heated to millions of degrees. This gas provides a medium through which sound can travel. The black hole's jets, streams of matter and energy blasting outward at nearly the speed of light, were creating pressure waves in this gas, ripples spreading outward like rings in a cosmic pond. and those ripples were sound waves, but the frequency was staggering. The note produced by the Perseus black hole is a B-flat, 57 octaves below middle C. It has a period of about 10 million years. One single vibration takes longer than all of recorded human history. To make it audible, NASA scaled it up by 57 and 58 octaves, increasing the frequency by 144 quadrillion times. What emerged was that haunting, ghostly moan that captivated millions. This is different from other sonifications. This was not just data translated into sound. This was real acoustic waves, detected and amplified. The Perseus black hole is genuinely humming. We just needed technology to hear it. Sonification lets us hear distant objects through translation. But what about actual microphones in space? In February 2021, NASA achieved something unprecedented. The Perseverance rover landed on Mars carrying 2 commercial microphones, the first dedicated audio recording equipment ever sent to another planet. And then it started listening. The first recording was humble, a low growl of Martian wind, barely audible over the mechanical hum of the rover itself. But it was the first natural sound ever directly recorded from the surface of another world. Since then, Perseverance has built an astonishing audio library. It has captured dust devils swirling past. You can hear the pressure drop as the eye of the tiny storm passes. Then the wind picks up again. It has recorded its own wheels crunching over Martian gravel, and the metallic scrape and clatter of an aluminum rover navigating rocky terrain. It has recorded its laser-zapping rocks, each pop giving scientists clues about the hardness and composition of the target. And in April 2021, it recorded something even more remarkable: the buzz of the Ingenuity helicopter's rotors hovering in the thin Martian atmosphere 260 feet away. Sound travels differently on Mars. The atmosphere is about 1% the density of Earth's, and it is almost entirely carbon dioxide. Sounds are quieter, more muffled, with bass frequencies traveling farther than high pitches. If you could stand on Mars without a spacesuit, voices would be harder to hear, and they would have a strange, dampened quality. But sound does travel. Mars is not silent, and for the first time, we can hear it. There is another kind of cosmic sound that does not require air or gas at all. On September 14th, 2015, at 5:51 in the morning Eastern Time, a signal arrived at 2 detector facilities in Louisiana and Washington State. The signal lasted 0.2 of a second. It started low, rose rapidly in pitch, then abruptly stopped. Scientists called it a chirp. That chirp was the sound of 2 black holes colliding 1.3 billion years ago. The detector that caught it is called LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO does not detect sound waves or electromagnetic radiation, and it detects gravitational waves, ripples in the fabric of space-time itself, predicted by Einstein a century earlier, but never directly observed. When massive objects accelerate, when black holes spiral into each other, when neutron stars collide, they create waves that stretch and compress space as they pass. LIGO's laser beams can measure these distortions to within 1/10,000th the diameter of a proton. The September 2015 detection was 2 black holes, each about 30 times the mass of the Sun, spiraling together and merging. In the final fraction of a second, they released more energy than all the stars in the observable universe combined. And that energy rippled outward as gravitational waves that, 1.3 billion years later, gently jostled the mirrors in LIGO's detectors. Gravitational waves are not sound, but their frequencies fall within the range of human hearing. When scientists convert the detector signal directly to audio, you hear that characteristic chirp, the pitch rising as the black holes spiral faster and faster, then cutting off at the moment of merger. It is the universe ringing like a bell, and now we can hear it. Perhaps the most poetic sounds from space come from the edge of our solar system, and beyond. Voyager 1 was launched in 1977. 46 years later, it is still transmitting. It is now over 15 billion miles from Earth. Farther than any human-made object has ever traveled. In 2012, Voyager 1 crossed a boundary that no spacecraft had ever crossed, the heliopause, where the sun's influence ends and interstellar space begins, and its plasma wave science instrument recorded the transition. Inside the heliosphere, the bubble of solar wind surrounding our solar system, the plasma produces low frequencies around 300 Hz. When Voyager 1 entered interstellar space, the frequency jumped to between 2 and 3 kHz, corresponding to the denser gas in the interstellar medium. Scientists called it the sound of interstellar space. The recordings are triggered by solar events, when coronal mass ejections, massive eruptions from the sun, reach Voyager's location a year or more later. They excite oscillations in the surrounding plasma. Think of it like fingers strumming a cosmic guitar string. What you hear is a rising tone, an ethereal hum from the space between stars. It is haunting precisely because of what it represents. Data from a region that no human will likely visit for centuries, converted into something we can experience with our own senses. And Voyager carries another kind of sound, intentionally placed. The Golden Record, attached to both Voyager spacecraft, contains greetings in 55 languages, music from Bach to Chuck Berry, and a sonic collage of earth, thunder, wind, birds, whales, a baby's cry, a kiss. It carries a message from humanity into the cosmic deep, traveling at 17 kilometers per second toward an unknown future. So here is what NASA does not always make clear when they release these recordings. Almost none of this is what you would actually hear if you were there. The Perseus black hole moan has been shifted up by 57 octaves. The gravitational wave chirp has been amplified and converted from space-time distortion to speaker vibration. The galaxy sonifications are artistic interpretations of light data. Even the Mars recordings, while genuinely acoustic, would be extremely faint to human ears standing on the surface. Does that make them less real, less meaningful? Absolutely not. Consider this. When you look at a Hubble image of a nebula, you are not seeing what your eyes would see. Much of that light is infrared or ultraviolet, invisible to humans. The colors are assigned by scientists to represent different wavelengths or temperatures. Yet we accept those images as showing us reality, because they do. They reveal truths about the universe that we could not otherwise perceive. Sonification does the same thing for our ears. The human sensory system evolved to navigate African savannas, not to comprehend galaxy clusters or black holes or gravitational waves. We cannot see X-rays. We cannot feel space-time curvature. We cannot hear a note that takes 10 million years to complete one vibration. But we can build instruments that extend our senses. And we can translate what those instruments detect into experiences that our brains can process. Images of infrared light, sounds of gravitational waves, music made from the death of stars. There is another reason NASA invests in sonification. Sometimes you can hear patterns that you cannot see. Dr. Kimberly Arcand, the visualization scientist at the Chandra X-ray Observatory, who leads NASA's sonification project, describes it this way. Sound is a time-based medium. It unfolds sequentially, revealing structure as it progresses. Images show everything at once. Sound tells a story. In one citizen science project, high school students listened to sonified data from Earth's magnetosphere, the magnetic field that protects us from solar radiation. By listening carefully, they identified a distinctive sound that the scientists had missed visually. When researchers investigated, they discovered it was a coronal mass ejection arriving at Earth, a solar storm that could have affected satellites and power grids. The students heard something important, hiding in the data. Sonification also makes space science accessible to people who are blind or have low vision. For the first time, these audiences can experience Hubble images, feel the difference between X-ray and infrared observations, and explore the cosmos through a sense they can fully use. In this way, turning space into sound is not just a gimmick, It is a genuine scientific tool and a profound act of inclusion. There is something deeper here, something almost philosophical. The ancient Greeks spoke of the music of the spheres, the idea that celestial bodies produce harmonious sounds as they move through the heavens. They believed the cosmos was fundamentally musical, that mathematics and harmony governed the universe. They were more right than they knew. The universe is filled with vibration. Pulsars, rapidly spinning neutron stars, emit radio pulses with the precision of atomic clocks, some hundreds of times per second. Stars oscillate, their surfaces rising and falling in patterns that reveal their internal structure. The cosmic microwave background, the afterglow of the Big Bang itself, carries temperature fluctuations that, when sonified, produce a cosmic hum containing information from the birth of the universe. Gravitational waves turn colliding black holes into cosmic drums. Plasma waves make the sun and planets ring like bells. Even the apparently silent vacuum thrums with quantum fluctuations, virtual particles popping in and out of existence at scales too small to measure directly. The composer, Sophie Kastner, has worked with NASA's sonification team to turn their data into actual sheet music that can be performed by orchestras. The resulting pieces are not just pretty, they are scientifically accurate representations of data from the galactic center, the Crab Nebula, and other cosmic objects. Imagine that, a symphony orchestra performing music written by the death of stars. So let us revise what you learned in school. Sound cannot travel through a vacuum, but the universe is not entirely vacuum. Galaxy clusters roar with acoustic waves. Planetary atmospheres whisper with wind. Plasma oscillates throughout the solar system and beyond. And where true sound cannot exist, other forms of vibration take its place. Light carries information we can translate. Gravitational waves ripple through space-time itself. Instruments extend our senses into realms evolution never prepared us for. The universe is not silent. It is vibrating at frequencies we are only now learning to detect, filled with rhythms and harmonies that span octaves from attoseconds to millions of years. We have been deaf to it not because nothing was happening, but because we did not have ears that could hear. Now we do. Every sonification NASA releases is a window into this hidden acoustic universe. Every chirp from LIGO, every recording from Mars, every translated pulse from a distant pulsar tells us that the cosmos is alive with motion, with energy, with something that, translated into human experience, we can only call music. The next time someone tells you space is silent, you can tell them the truth. Space is full of sound. You just need to know how to listen. There is a black hole 250 million light years away, singing a note so deep it takes 10 million years to complete one cycle. There is a rover on Mars recording the Martian wind, the first mechanical ears on another world. There is a spacecraft at the edge of interstellar space, still transmitting after 4 decades, carrying both the sounds of humanity and recordings of the void between stars. There is a pair of detectors on Earth that can hear the universe ring when black holes collide billions of light years away. And there are scientists who take all of this, the light, the gravitational waves, the plasma oscillations, and translate it into something we can experience, not to fool us into thinking space sounds like a symphony, but to reveal that, in its own way, it does. The music of the spheres is real. We just needed to build instruments sensitive enough to hear it. And now that we can, the cosmos will never be silent again.